Welcome to Target IAS. I am Prakash Rajput and today we will see few things about dielectrics. So, in case of conductors, there are large number of free charges, that is electrons are there in case of conductors. And in case of insulators and dielectrics, the charge carriers, or you can say electrons, are not free. But in case of dielectric, if electric field is applied electric field is applied, then the charges forms dipole. When electric field is not equals to 0, these charges will form dipoles. The negative charge, that is electron, suppose here I apply the electric field from positive to negative, so the electron will try to move in this direction, and the positive charge of the nucleus will try to go in the positive direction, but they cannot move. They can only they can induce charges. So here charges will be induced. Actually charges was already there, but they are little separated now, so they will make dipoles. And this thing in the dielectric will make the dielectric special. So what is this speciality? This leads to this will help in storing energy in the dielectric. This will help in storing the energy in the dielectric. In the it will store electrostatic energy. And as I've told earlier also, that this process, when the electric field is applied and formation of dipole, this is called as polarization. This is called as polarization. And this dielectric is said to be in this condition as polarized dielectric. So, and I have defined polarization earlier also. What is that? The formation of dipole. So here many number of dipoles are there in the dielectrics. The polarization is, so a dipole moment of the dipole is a small value. So for on a large scale, if we want to say about dipole moment, so it is given by polarization. So polarization is basically total dipole moment. Total dipole moment, that is qi di, total dipole moment per unit volume. This will be the value of polarization. This will be the value of polarization. So here I am writing capital P. Don't get confused with small p of the dipole moment. So this is basically polarization. Now if you see that it is having unit q into d, it will be coulomb meter, and divided by volume will be in meter cube. So unit will be coulomb per meter square. It is basically the unit of electric flux density, if you remember, electric flux density. So when a dielectric is polarized, or we can say the polarization increases the electric flux density inside a dielectric. So earlier it was just epsilon naught E, but due to polarization the value becomes this: D is equals to epsilon naught E plus P. This was earlier, and this is due to what? Dipole formation. This is due to dipole formation. So this extra term, which is polarization, is also defined as epsilon naught xi E, electric field. This is the value of polarization. This is the value of polarization, where this xi is called susceptibility. Where this xi is called susceptibility. Susceptibility of the material, that is how easily it can be polarized. So this is the value of P. If I put this value here in place in the equation of D, what it becomes? Epsilon naught E plus, here I will write in the place of P epsilon naught xi E. So you can take epsilon naught E common, and what is coming? 1 plus xi. And if you have idea about d is equals to, when a dielectric material is placed, the epsilon naught gets replaced by its relative electrical permittivity E. And if you compare these equation, you will get that epsilon r is equals to 1 plus xi. So this is also a useful thing. This thing you will learn more in detail in the electrical materials. So here this is the expression of d is equals to epsilon naught r into E. Here this is also expression which can be used, and we can find many expression using uh, all these three. Like if I can relate the displacement flux density only in terms of polarization and electric field, only in terms of polarization and electric field. Suppose if I take p common from here, so what is remaining? If I take p common, so 1 will remain, and epsilon naught E divided by p, this will be remaining. So in place of this I can write 1 plus epsilon naught E. I'm writing all in vector form, so I will write this in also in vector form. And p, you know that what, epsilon naught E xi. So this thing and this thing will get cancelled, and I can write this expression as this also. So many expression can be written for d, e and p using all these simple ones, like the first one and this one and this one. Okay, so these are main expressions for the electric flux density and for polarization. Now here if you see, potential battery is connected across these conductor plates. So here this current starts flowing. This is basically what, conduction current. Conduction current. And you know that conduction current is given by rate of charge of rate of flow of charge, that is dq by dt. So in a conductor we know that this Ic is given by dq by dt, and if you want to write the expression for its current density, it will be Jc by Jc equals to Ic divided by A. So also in conductors it is also sigma E, you know that. So now here what is happening, this charge is getting positively charged, and here is negative. So what happens is, here the electric field will set up and flux starts moving from this to this. So here there cannot be a rate of charge, right? Rate of flow of charge, there cannot be rate of flow of charge, because this is like not a conducting medium. So what happened here is, so here no current will be flowing, only there will be rate of flow, rate of change of flux, rate of change of flux d psi by dt, which will constitute a current that is known as displacement current, that is known as displacement current. So this displacement current, if I write in the form of displacement current density, it will be id by a. So it will be d psi by dt by a. And you know that I can write this as d by dt of psi by a. So what is this psi by a? Flux upon area, it is displacement flux density, right? So I can write this as like this. So here this is displacement current density. So the displacement current density is given by jd is equals to dou d by dou t. You can also remember this equation for the displacement current density. Okay, so displacement current density is given by jd is equals to dou d by dou t, or del d by del t, you can say. Now we will see the next topic is capacitance. Is capacitance. If there are two, suppose, metal plates, one having positive charge, one having negative charge. So what happen is, the flux will start going like this, like so there will set up an electric field. So the electric field will be going from positive to negative. This means that there is some potential difference across these. Suppose this conductor A and this conductor B having plus q charge and here minus q charge. So this is having some potential VAB. VAB, right? So capacitance is defined as between these two suppose plates is defined as the total charge on either of the plates divided by the potential difference between them. This will be the value of capacitance. This is the definition of capacitance. Capacitance is defined as the total charge on either of the plate divided by the potential difference between these plates. So using this the you can find the for different configurations capacitance of different configurations. So first let us find a simple one, that is parallel plate capacitor. Parallel plate capacitor. So for a parallel plate, what I have to consider is parallel plate having some positive charge density, suppose rho s, and a negatively charged plates of same dimensions having surface charge density as minus rho s. So what happened here is electric field will start going like from here to here, and for a infinite surface charge density, the electric field will be what? Rho s by 2 epsilon. Rho s by 2 epsilon. Not suppose I'm not taking any dielectric material between them. So what happened here is because of this rho s by 2 epsilon naught, and because of this negative charge also there will be in the same direction rho s by 2 epsilon naught. So total electric field is rho s by uh, epsilon naught in this region, rho s by epsilon naught. And if I take this direction, some direction of like an cap, okay. Now what is capacitance? Capacitance will be q by v between these plates, and q will be what? Rho s into area of these plates. Suppose this charge is uniformly distributed, so I can take the area as a, or otherwise I have to what? I have to do integrate like rho s ds, surface integral of rho s ds. So but I'm assuming that it is having uniform surface charge density, so I can directly write rho s into a, and in place of v I can write in minus integral of e dot dl, minus integral of e dot dl. So it will be rho s by epsilon naught. Here this dl vector I can take, so and it will be like this, okay. E dot dl. So e is in the direction of an, and dl is also like I'm going in this direction, so dl and al are in the same direction. So this dl is nothing but, if I integrate this dl, is nothing but this distance which will be here. And if I take here an cap, so in this direction what it will be? Minus an cap, right? So you can simplify it, and after simplifying you will get what? Rho s a by rho s epsilon naught from here, and for dl this distance will come, and you will get a formula like this: epsilon naught a by d for a parallel plate capacitor which is having no dielectric between its plates. If a dielectric is placed, then this epsilon will be replaced by what? Just this epsilon naught will be replaced by just epsilon a by d. Epsilon a by d, where this epsilon is equals to epsilon naught epsilon r, epsilon r is what? Relative electrical permittivity of the dielectric. So this will be the expression for parallel plate capacitor. So you can find capacitance of any configuration which is given, using the simple formula, which is C is equals to Q by V, this formula. So let us see one more configuration. Now let us see capacitance of a coaxial cable. So this is basically a coaxial cable having an inner conductor surface charge density rho si. Suppose this is having rho si and this is having surface charge density rho s naught. We have solved the electric field for a coaxial cable. If you remember this, so this is the electric field for a coaxial cable, and this is the expression rho si into a upon epsilon naught rho. This is the expression for electric field due to coaxial cable we have taken earlier. So we have solved this problem for coaxial cable, finding the electric field due to coaxial cable, if you remember. So now let us uh, uh, let us take this cable again and use that result of the electric field. So this was the cable having rho si as the inner conductor surface charge density and rho s naught for the outer surface charge density, and we can find the charge using these formulas, and this is the expression for electric field between the coaxial cable, the from A to B. Okay, so it is rho s I a rho s I into a divided by epsilon rho. So I am taking in this case a dielectric material. तो एक जनरल केस हो जाएगा. जब डायलेक्ट्रिक मटेरियल नहीं होगा तो यू कैन टेक एप्सिलॉन नॉट डायरेक्टली, एंड डायलेक्ट्रिक मटेरियल होगा तो एप्सिलॉन प्लेस कर देंगे. So here this direction is aero cap, and this is for A to B region, in the region A to B, because in that region I have to calculate the capacitance only. So as from the definition of capacitance, what is that? Q by VAB. Basically we are finding CAB. So this will be the value. So for Q, what will be the, now this time I will integrate because surface charge density. So it will be what? It will be rho si into rho si into ds. So what will be the ds for this surface? It will be rho d rho d phi. Here the changing things are uh, no, wait, we are taking curved surface area, right? So the unit vector will be in the direction of aero cap. So the surface, differential surface which I have to take is rho d phi dz, rho d phi dz, and for VAV it will be minus integral of E dot dl. So E is nothing but rho si into a by epsilon rho. Here it will be dl. So what will be dl? So as I'm going from A to B, so dl is rho d rho, right? Rho d rho, not rho d rho, only d rho aero cap, and here also aero cap. So dot product of aero cap will become 1, and solving this here, solving the upper integration, rho si will come outside the integration, rho will also come out of the integration, right? Here as this is this is what, this is surface charge density for inner surface, so I can write in place of rho as a, and integral d phi where limits from 0 to 2 pi, and dz where limits from whatever the length of the coaxial cable. So I can take let us take the length of the cable is h, divided by here rho si will come out minus rho si. Epsilon will also come out, and the other thing which will come out is a, right? So a will also come out, and arrow is becomes ones, and what is remaining? Remaining is 1 by rho t rho, and the limits are from a to b. Limits are from a to b. Solving this, so rho si will cancel and a will get cancel. So and this epsilon can go up, and after solving this d phi will be coming phi and putting the limits, so it will be 2 pi. Here it will be h, and 1 by rho integration will be ln rho, and here limits are from a to b and a minus sign. So after solving this will come as what? 2 pi epsilon h. Here we are finding VAB, right? So for VAB I have to put lower limit as B and upper limit as A here. This mistake I have done, you can correct it. So here also the limits will be from B to A. So after solving this will come as ln B minus ln A, a minus sign. So after simplifying this, the capacitance due to a coaxial cable, it will be coming as ln B by A. ln B by A. I have written again this. So here this will be ln A minus ln B, and after simplifying this will be coming ln B minus ln A, and after using the log property, this will be the expression of capacitance due to coaxial cable. This will be the expression of capacitance due to coaxial cable, 2 pi epsilon h upon ln B by A. This is unit farad. If I want to write in farad per meter, then I have to take this h downwards, so I can write the expression for capacitance in farad per meter also, 2 pi epsilon upon ln B by A. Hope you understood it. Right. Now let us take one more configuration of capacitance to find the capacitance. So let us find capacitance due to spherical capacitor. So suppose this sphere, inner surface, inner sphere having positive charge q. So this outer surface will be having some negative charge induced on it, right? So this will be having like negative charge on it, so minus q. So due to this they will have some potential difference VAB, which can be what? Written as minus integral B to A E dot dl. And you know that electric field for this surface can be written as what? Q by 4 pi epsilon naught r square ar cap in the region A to B, right? So in the region A to B, you have already known to this. So we can apply the definition of capacitance, that is charge on either of the surfaces, whatever it is. So it is here spherical surface, so I have taken either of the charge magnitude divided by VAB. And what is VAB? Q by VAB is this minus integral B to A, and E value is Q by 4 pi epsilon naught r square AR cap. So what will be the DL vector? What will be the DL vector? It will be again what? DR AR cap, because here AR, so AR cap will be required, right? So it will be Q by, and you can simply cancel Q, in fact. So this Q will come out of the integration because it's independent of the R. So Q and Q will get cancelled. Here 4 pi epsilon naught will also come out, and here I will take a dielectric medium inside this these spheres. So here this expression will be more general, so it can be written as 4 pi epsilon, and only thing remaining are 1 by r square dr from B to A. So after simplifying this, integrating it, what it will be? It will be minus 1 by r from B to A, and here this minus sign is also there. So I can write 4 pi epsilon naught 4 pi epsilon 1 by A minus 1 by B. So this is the value of spherical capacitor. This is the value of spherical capacitor, 4 pi epsilon upon 1 by A minus 1 by B. Okay. So due to a spherical capacitor, this will be the value of spherical capacitance. If suppose this B tends to infinity, if B tends to infinity, then this term 1 by infinity will become 0, and the capacitance will directly become 4 pi epsilon A. So this is the value of spherical capacitor, or you can say an isolated spherical uh, capacitor. Okay, so this will be the value of for spherical capacitor when B tends to infinity. Now let us see another topic, capacitance in series. Now you have learned in networks, and many of you might know what happens when capacitors are in series. It can be replaced by an equivalent capacitance of C, whose value is given by 1 by C1 plus 1 by C2, and if you do the whole inverse, right? Or you can write C1 C2 upon C1 plus C2. So what actually happen here is, if the capacitors are connected in series, suppose here this is a battery and here is one capacitor, right, and here is another capacitor. These are two capacitors, C1 C2. Okay, so what happen here is, if you see that this is potential V, and across this potential difference will be V1, and across this potential difference will be V2. Now you know that this will be having some charge flowing through this, and here the displacement current will be there. So you can see that displacement current ID is constant, and what is other thing which are constant for these two capacitors? Here you can see that q q is also constant, flux for all these will be constant, right? So you can and also one thing, that area of these plates is also constant, like it is not divided by these two capacitors, right? So id and psi and q are not divided, are not divided when the capacitors are connected in series. But what are the things which are divided? The potential difference. So the total potential difference V is equals to summation of, that is addition of uh, both the potentials on the individual capacitors. So you can see here, if I make this capacitors like here, it is having some d1 distance, and here it is having some d2 distance. Suppose it is having epsilon naught permittivity and epsilon 2 permittivity. So what you can think of, this capacitors is a parallel plate capacitor, and its value will be epsilon A divided by d1. And what will be the value of C2? It will be epsilon A divided by d2, right? Epsilon A. So what are the things which are dividing? The distance, right, and V and E. So here you can see that the total distance is d, and which can be written as d1 plus d2, and total potential is V, which can be written as V1 plus V2. Now if you know that what the total capacitance is, C is equals to Q by V, right? So Q by V is nothing but V1 plus V2, and I can write V in terms of, like, if Q equals to C1 V1, right, from the same expression I can write. So it will be what? Q by, in place of V1 I can write Q1 by C1 plus, here these all are in denominator. So here in place of V1 it will be, here in place of V1 it will be Q by C1 plus, and in place of V2 it can be simply C2V2. So in place of V2, Q by C2. Now you see that the total capacitance which was coming earlier was 1 by C1 plus 1 by C2 when they are connected in series. They are connected in series. That's why they are coming like this. Okay. So here you can remember one thing, that the displacement current is not dividing. Q is same and flux is same and area is same for capacitors which are connected in series. Okay. Now we can take another thing here. One more combination is also there. Parallel capacitors connected in parallel. So what happen in case of when capacitors are connected in parallel? So capacitor, let us take two capacitors which are connected in parallel. Two capacitors which are connected in parallel, and you know that they can be replaced by an equal capacitance whose value is C, and that will be C1 plus C2. Now in this case, if you see what are the things that are dividing, so here you can see the D, the distance D is not divided. Okay, so D is not divided. Also, if you see that it is, if they are connected to some potential here, so here you can also see that V and E are not divided. V and E are not divided among them, because across this also same potential, across this also same potential. So as D is also same, so the E1 for this capacitance will be what? V by D, and for this C2 it will be again what? V by D. So same. So V and E are not divided. So what are the things that are that will be dividing? As you know that total current will be something, and it will be dividing here. So the displacement current in this capacitor, here ID1, here ID2. So ID gonna divide, right? And similarly, as the I is dividing, the charge will also divide, right? And similarly the flux will also divide. So here you can write that ID, flux, Q are divided, right? ID, Q, flux are divided. Okay, so now you know that what? That ID is what? ID1 plus ID2, and ID1 is what? D psi 1 by dt plus D psi 2 by dt, right? And the psi 1 and psi 2 is are nothing but the charges only, right? I can replace this as dq1 by dt or dq2 by dt, right? Now this q1 what it will be? It will be c1 v, because potential is not dividing, right? q1 will be c1 into v, and q2 what it will be? C2 into V. So total charge will be what? Q1 plus Q2. So I can write it as C1 V plus C2 V. I can take V common and write it as C1 plus C2. And what this will be? Q? Q will be the total capacitance into the potential. So if you see here, what it's coming, the total capacitance value is for series combination. It is the the capacitors which are sum of the capacitance which are connected in parallel. Okay, so that's how the this combination of series and parallel works. So if you think of some capacitor connected like this, and here in place of this, one dielectric is placed and other one is not placed. Suppose this is my first case which I am writing here. In this case, the distance is d and the capacitance here, suppose its area of the plates is a. So what will be the capacitance? It will be some epsilon, uh, epsilon naught. Suppose air is there only, so epsilon naught a by d. Now for this case, what happened here is that the distance got divided. The distance got divided. So what is this? What it this will be like a combination of two capacitors which are connected in series. So here this will be C1 and this will be C2, where C1 will be k times epsilon naught a by d by 2, because the distance is d by 2, and C2 will be epsilon naught a by d by 2. And what is the total capacitance? What is the total capacitance? That is, for series combination, it is C1 C2 by C1 plus C2, right? So you can solve this expression as like k epsilon naught a by d by 2 plus epsilon naught a by d by 2, wait, there it will be C1 C2 multiplication divided by addition. Now k epsilon naught a divided by d by 2 plus epsilon naught a divided by d by 2. Okay, now you can simplify this. What will come? It will be, you can take few things common, like epsilon naught a by d will get cancelled if you take this thing from here, and the thing which will remain is here it will be 2k and here it will be 2. Also I can take epsilon naught d by 2 actually common, so the remaining thing is on the upper part, it will be 1 epsilon naught a d by 2, and here I have taken k plus 1, right? So this will be the value of, I can write 2k by k plus 1 epsilon naught a by d. So this was my original capacitance. Now you can see that this will be the value of capacitance after putting a dielectric medium in between the capacitor. So here is this one question. In this, these are conducting plates in which this dielectric is placed epsilon r1, and here one dielectric is placed epsilon r2 of permittivity epsilon r2, and said that total capacitance of this combination is 60 nanofarad, and the value of epsilon r2 is given to be 2.5, and we have to find this value of epsilon r1. Okay, so what it looks like, that it is a series combination or a parallel combination. What is this? So you can see that d is not divided, the area is divided, right? Area is divided. These are square plates, the area is divided. So as the area is divided, we can think of this combination as two parallel capacitor. One is C1, one is other one is C2. So what will be C1? It will be epsilon r 1 into a 1 by d. So a1 will be, here this is a square plate, so total this length is 2, and along this line will be, there will be, like, if you see, imagine this, these square plates are like this. Okay, so these will be having 2 by 2 area as given. Okay, so for the epsilon r1, or we can say c1, the area will be 1.2 into 2. So epsilon r1 I have to find out, and the value of area will be 1.2 into 2 uh, divided by, here epsilon naught is also there. Okay, just not epsilon r1, and the d value, d is no given, the d value is actually 2 mm. I forgot to write. So d value is 2 mm, 2 in 10 to the power minus 3. So after solving this, what I will get in terms of epsilon naught and epsilon r, it will be 1.2 10 to the power 3 1.2 10 to the power 3 epsilon naught epsilon r 1. Okay, now I will find C2. It will be epsilon naught epsilon r2. Epsilon r2 is nothing but 2.5, and the value of a1, it will be 0.8 into this length 2. So it will be 0.8 into 2 divided by the d will is same for both these capacitors. So 2.5 into 8, 0.8 into 2 divided by 2 into 10 to the minus 3 is 2000 epsilon naught. 2000 epsilon naught. Now for capacitors to be connected in parallel, the answer is adding them in. Total capacitance will be given by adding them. So 1.2 into 10 to the power 3 epsilon naught epsilon r1 plus 2000 epsilon naught will be equals to what? Will be equals to, given question is 60 nanofarad. 60 nanofarad. So I can write here 60 nanofarad. And after putting the value of epsilon naught, what is the value of epsilon naught? It is 8.854 10 to the power minus 12. Okay, so it will be 1.2. I better write this as 1200. So 1200 epsilon r1 plus 2000 equals to, on the right hand side I have solved this as 677 6.6. Okay, and after solving this minus 2000 and dividing it by 1200, the value of epsilon r1 coming is 3.98. 3.98, that is the required value of epsilon r1 in the question. So that will be all for today. We'll meet in the next lecture.